49. Whoops, got to turn your calculator on first. How many people do that routinely? You start typing numbers and oops, it's not on. I feel not quite so senile. All right. Do you guys get something like 79.4? There we go. Now, this is somewhat interesting. A somewhat interesting thing is that the tension in that cable, and there's two of these, the tension in that cable is more than the weight, right? But that's because of the geometry of this. These little triangles are low and lean, and they've got mostly horizontal component that's just pulling against each other, and very little of them is vertical, so it's not very efficient, right? This is not a very efficient way to lift a load, correct? Now, when you look at those bridges, I don't know if you guys have seen these bridges. I'll erase the stupid equation, right? But there's a bridge like this right by the campus, right by the Union Station in Portland, and they've got a support there and a support there. These things are held down by giant guy wires, and then they've got these little things that go like this, right? You've got to wonder, these cables that are pulling to the side like that are mostly pulling sideways, aren't they? Right? And they're not pulling up very much, right? Well, what you've got to understand, it is an artistic statement. It's not an efficient way to design a bridge. But don't worry, steel is really, really strong in stretching. It's very hard to stretch steel, so it's very, very strong has a lot of tensile strength, right? And then if this deck is made of something like concrete is going to be compressed by those forces, but it's also very strong like that, right? So it's not the most efficient thing. When you see suspension bridges, of course, what they do in really big, long, serious ones is they stretch a big cable like that, and then the lines that come down to it come straight down so that all of that tension going up is straight up, which is what you want, right? But it doesn't look quite as nice, does it? You know? Okay, now just for fun, let's make this angle smaller. Let's make it 5 degrees. What's going to happen to the tension if it's 5 degrees? Well, to make it have the same amount, I've got to draw way, way longer, right? So do the same thing here and make that 5 degrees, right? What do you get for this? Go second entry, take your calculator, go second entry, and go back and edit the 18 and make it a 5. What do you get for your force? 281, that's a lot more force. It was, 79.4 with 18 degrees, right? Okay, 5 degrees gives us 281.4. Is it always 0.4? Okay, try 1 degree. We're talking. Let's not talk. Let's try 1 degree. Go second entry. Yeah, that's a lot, isn't it? All right. Yeah, they're both here. Are we good? Do y'all get 1,405? So here there's two things. There's two things, and these are interesting things. Okay. The first one is that what is that approaching? As the angle, I want to pass that back. As the angle approaches 0, what does the tension need to be to hold up some weight? What is it approaching? If we put in 0, what are we going to get? If we put in 0 for this angle, what do we get?
Not possible.
Yeah, we get all the mathematicians say that it's undefined. Okay, but it's infinity, correct? Isn't the answer it's infinity? Yes. So what this means is this, okay? If you have a tightly stretched cable, let's get rid of, we'll ignore the weight of the cable, right? But let's suppose you have a tightly stretched cable. If a flea lands in the middle, it will deflect. Even a steel cable with thousands of newtons of force in it, right? A flea lands in the middle of it, it will deflect downward. It has to. There has to be some angle, right? And then the other thing is that if we've got a cable stretched like that and we push in the middle of it, don't we exert a tremendous force? Don't we change the tension by a lot? Yeah, that's sort of an interesting thing. So this is the poor man's winch. If you've got a road, you've got a car that you want to pull back onto the road, like this, right? One of the things you can do if you don't have a winch, if you have a winch, you tie the winch to a tree that's in the direction you want the car to go, and you turn the winch on and it pulls your car back on the road. If you don't have a winch is like this really powerful thing that winds it up on a spool, right? Okay. If you don't have a winch, this is what you do. You stretch the cable from the frame of the car to the tree, and if you've got some knot that you can put it in to tighten it, or if it's a chain, you tighten it by pulling the links through, right? And then you just push in the middle. Well, at first, what's that angle before you've deflected it? 0, so the tension you cause is what? Well, technically it's infinity, but the cable stretches and it becomes some small angle. At first, that's a small angle, isn't it? Isn't your force tremendous? Yeah, something's going to happen. If you stretch a chain tightly between there and you push on the middle, the tree's going to fall down, the car's going to move, or the cable's going to stretch or break, right? So if you have a strong enough, unstretchy enough cable and you push on it, this car is going to inch its way down. And then what happens is, of course, the angle gets big, doesn't it? The force drops. Don't you have to tighten up the rope? Right? So that's the procedure, right? You just tighten the rope up, push on the middle, tighten the rope up, push on the middle. Eventually you're going to work that thing onto the road. That's kind of cool, huh? Yeah. Yeah, it could be the tree could fall in the car. You know. The other thing you could do, by the way, is if the cable comes off of here and you can't reach the tree, but you can reach the branches of the tree, you could throw the cable up into the branches of the tree. And then if you forget about the winch, if you've got an electric winch, you come back and the car is going to be hanging in the tree, right? How many people have seen that movie? Nobody's seen that movie? Gods must be crazy. Yeah, there we go. Okay. Look how fast you're learning. Go, you stupid thing. Okay, there we go. So write that one down. This is the next one we're going to solve. And this one is asymmetrical. This one is not going to be, one of the equations won't be solvable. We're going to have to solve simultaneous equations with a matrix. Okay? Yeah. Yeah, that's sort of a cute little story interspersed with like senseless violence. Let's make it look nice here. This guy's a 20-degree angle. What's with these like nuclear pen caps? Is that level? That's sort of level. Here's 20 degrees. So this angle here is 20 degrees, this angle here is 40 degrees, right? 12.5 kilograms is hanging on this thing, right? This is going to be asymmetrical. It's not going to be simply solvable. We're going to have to use both equations. So it's the worst possible case scenario, right? So step by step, what do we do? Our first step is to... Yeah, let's calculate the weights just for fun here, right? So, and this is also harder because 12.5 times 9.81, we haven't done that one very recently, right? Okay, so 12.5, the force downward is 12.5 times 9.81, and I'm getting that downward force is 122.625. Yeah? So that's the downward force here. I'm just going to draw a little arrow there. Okay? And then our next step is to, and I'm going to draw these, and I'm going to try to do a good job of drawing them. Okay? Let's draw a sideways component. What's true about these sideways components?